Okay, so we make the examples for second order ODE with the shooting method to solve the BVP problem. Now we will transfer to a higher order ODE. Okay, for higher order ODE with BVP conditions, we can still use the shooting method. It's very similar to the second order ODE. The first step will be still convert nth order ODE into n first order ODE and write as a state space representation. Okay, so we will have, for example, z equals to y, y prime, y double prime until yn minus 1, and this z will be z1, z2 until zn. Second, after we write the state space representation, we know what kind of initial conditions we have. We also know what kind of initial conditions we are missing based on the boundary conditions. So we identify our n conditions. And we know at point 1, at a point, we can say the initial point is x1. We have n1 conditions. At point 2, we have n2 conditions, where this n2 will be n minus n1. Okay, so that we have enough conditions to solve the ODE. Then, since we don't have enough n1 conditions, we need to guess that n minus n1 conditions for the initial point. We will guess alpha will be the same size as n2. Okay, we will guess alpha. So z at p1 will be equals to z p1 alpha naught, and this naught means the iteration number. So number of iteration. Okay. So we know we have at p1 point we need all n conditions. We have already n1. We need to guess that n minus n1, and this guess conditions we need to guess basically one iteration by one iteration to solve the error analysis to get the better alpha. Then in the end, we want to have our guess initial value to meet the final boundary conditions. Okay, so we will solve the IVP to get Z2 at P2, where Z will be P2 at alpha naught, this initial guess. Okay, we will solve the IVP with the initial guess conditions and get what is our P2, which is the second boundary, and we will do the error analysis. Where the epsilon k at initial step, the 0th iteration, will be z at p2 alpha 0 minus z at p2 true values. So these true values is based on our boundary value conditions. We have some points at P2 have these N2 conditions. We will compare to whatever we got solved P2 values based on these initial conditions. Then we will do the error analysis. If my epsilon k at mth iteration, so we will do those iterations until it will be smaller than the tolerance for all k, because you have z1, z2, z3 until zn, until all the z numbers, if that is all smaller than the tolerance, we are done. However, if one of them is over the tolerance, then we have to do another initial guess, right? So if epsilon k over tolerance for any k, then we need to give another guess. Okay, so we need to give another guess so that at mth iteration it will be all smaller than k. Then we are done. And how to give this new alpha new? So how to give this new? This alpha m plus 1 will be based on what current alpha plus this dot k. And this dot k is based on the arrow analysis, right? Where this dot k, a times dot k equals to epsilon m. Okay, I would say this is at mth iteration. We are trying to adjust whatever the current arrow opposite sign, so that the next guess is better and it can meet for the initial meet for the boundary conditions. With this a is equals to a I j equals to alpha I divided by alpha lambda alpha j. And you know this arrow analysis is based on the slope of the arrow as function of your guess. Alpha j will be equals to epsilon I at alpha 2 alpha j plus dot alpha j minus alpha I alpha 1 alpha 2 dot alpha n z divided by delta alpha j. So basically, we are trying to guess the future value based on whatever the current value with this arrow analysis. And this arrow analysis, this is basically stands for the slope of your current arrow as function of your initial guess. And run the ODE IVP until you epsilon k m smaller than tolerance for all k numbers, right? And for this j, the initial part you can do the perturbation, but next you will do, based on the perturbation value and the initial value, you can give a better guess. And based on the better guess, you can compare with the perturbation value or the previous initial value, give a new values. So that is similar to whatever we solved for the second order ODEs.